Hello and welcome to this video for CE108 Mechanics of Deformable Solids. So in the previous chapter we started to talk about the stress. So we defined stress and we saw how to calculate the stress within a material as a function of the external load that are applied to this body. So the stress is going to be the cause of the deformation of materials. The reason why materials are being deformed is because they are subjected to some stress. Now in this chapter, what we are going to focus on is not on the cause, but on the consequence of the stress. The consequence of the stress is that materials are going to be exhibiting some deformation. So in this chapter, we are going to talk about the deformation of materials. So we're going to talk about two things. First, how to quantify this deformation. And this is what we are going to do with the strain. The stress is what we the quantity that we define to characterize what is the intensity of load per unit of surface. And now we are going to quantify the deformation, the result of the stress. And this is what we are going to define with the strain, which is going to be the quantity that we use, the metric that we use to characterize how deformed a given material is. And then once we have a way to characterize, to quantify the deformation, then we will see what is the relationship between the cause and the consequence. So between the stress and between the consequence of the stress, which is the deformation. So we will see what is the relationship between the stress and the consequence, that is to say the strain. So let's start by getting some intuition about what is the strain and why is it the right way to characterize the deformation of a material. So for this, let's consider two beams, and let's assume that those two beams are attached to a fixed support, and the difference between those two beams is that one beam is 2 times longer than the other one. So you have one beam with size L and another beam with size 2L. And let's assume that those two beams are subjected to the same normal stress. So you have a normal stress sigma naught in both cases, which is the same. So in both cases, you apply the same load per unit of area. So you apply the same stress. So in this case, those two beams have the same cross-section. So if they have the same stress and same cross-section, it means that they also have the same load that is applied to those beams. So because of the fact that those beams are subjected to a tensile load, a tensile stress, those beams are going to be elongated. So their size is going to increase. So now if we look at how elongated those beams are going to be, so we can get some intuition about this. Like, for example, if you apply a stress that is large enough, so maybe the beam number 1 is going to show an elongation like this, and its new length will be L prime. And now when we think about the longer beam, it's our intuition tells us that the longer beam is going to be elongated more than the first beam. Why? Because this beam is longer. So because it's longer, it's easier to elongate it. So it's going to be elongated in total more than the first beam. So if we look at the elongation delta, so we're going to define the elongation delta, where delta is the difference between the new length minus the old length of the beam. And now if we look at the elongation in the beam 1 versus the elongation in the beam 2, then what we see is that the elongation of the beam is not the right quantity to define how deformed a beam is. Why? Because if those two beams are made of the same material, we see that here characterizing the deformation of this beam based on the elongation in meter or in centimeter or in inches by defining the length of this elongation is not a very meaningful is not a meaningful way of characterizing the deformation. Why? Because in this case it depends on the geometry of the beam. If the beam is longer, its deformation or its elongation will be also larger just because this beam is longer. So if we want a more universal way to define the elongation, to define the deformation of a materials, something that does not depend on its geometry, doesn't depend on its length, or doesn't depend on its size, we need to find a way to define, to characterize, to quantify the deformation of this body in a way that does not depend on its beam. And here, if we look at those two examples, if the beam is 2 times longer, if the initial length of the beam is two times longer, then it makes sense that its elongation delta 2 is also going to be 2 times longer than the elongation delta 1 of the beam number 1, which means that a more proper way, or a more meaningful way to define how deformed this beam is going to be to define not simply the elongation, but the relative elongation of this beam. Why? Because if your goal is to find a universal relationship between the stress that is applied on a body and its deformation, if you want to find a relationship between the stress and the deformation, and if you want this relationship to be generic, so that it does not depend on the geometry of the body, something that will only depend on what types of material this body is made of, then we need to find a way to characterize the deformation of this beam in a way that only depends on the material that this beam is made of, but not on the size, the length of this material. So in this case, again, those two beams are subjected to the same stress, sigma naught. So it's the same stress in those two beams. So ideally, we want to characterize the deformation of this beam, and the deformation should be the same. If the stress is the same, then the deformation, if we define this deformation properly, this deformation should be the same. So here in this case, the way that we are going to define the deformation is by looking at the relative elongation. If you look at the relative elongation, so you look at delta 1, this is the elongation of beam number 1, and you divide it by its initial length. So this is the relative elongation, the elongation divided by the initial length. So this is, in this case, elongation, and this is the initial length. And now if you look at this relative elongation for beam number 2, then this is the same, delta 2 divided by the initial length, and the initial length is 2L. Delta 2, we said that it should be 2 times delta 1. So what you see is that if you do that, the relative elongation of the beam in this case is going to be the same in beam number 1 and in beam number 2. If the beam is 2 times longer, then its elongation is also going to be 2 times longer. But when you define the relative elongation, then the relative elongation does not depend on the initial length of the beam anymore. It will only depend on which material is the beam made of. Is it, for example, steel? Is it concrete, etc.? And what is the stress that is applied to these materials? So what we find here is that if we characterize the deformation of materials not in terms of the absolute elongation in meter, inches, centimeter, etc., but in terms of the relative elongation, then we can get a more meaningful relationship between the cause of the deformation and the consequence, the deformation itself. Why? Because for one type of material and for one stress, then you will get one deformation. In this case, the deformation will be independent of the geometry of the body. It will be independent of the length of the beam. So this is what we are going to talk about in this chapter. We are going to see the relationship between the cause of the deformation. And in the previous chapter, we saw that the cause of the deformation, this is the stress. So for example, in the case of an axial load, we said that the stress is the load divided by the area. So this is only valid in the case of axial load. And what we are going to see now is what is the consequence of this. We are going to see what is the consequence of a stress being applied to a member. And what we see here is that the consequence will be a deformation, but the right way again to characterize the deformation is not simply the elongation of the beam, but it's going to be the relative elongation. So delta divided by L, or the change in length divided by the initial length of the material. This is the relative elongation. This is what we are going to call the strain. So in this case, this is going to be the normal strain because it's a normal deformation, and we are going to write it epsilon. Epsilon is going to be the strain, the relative deformation of the material. And the interest of characterizing the cause of the deformation in terms of stress and the consequence in terms of strain is that now this is going to be the relationship between the cause and the consequence. And this relationship between the stress and the strain will only depend on the material. So it only depends on the material that the beam is made of. It doesn't depend on the geometry. It does not depend on the geometry of the material. It will only depend on how stiff this beam is, what kind of material this beam is made of. Is it a stiff material or a soft material? And it does not depend on the length. It doesn't depend on the width of this beam, only on how stiff the material is. So now we are going to define more robustly what the strain is and how to calculate it. So in the same way that for the stress, we had the normal stress that tends to either elongate or shrink material, and the shear stress which tends to make the material being deformed clockwise or anti-clockwise by changing their shape but not their volume. Now we will have also two types of strain: the normal strain that characterize the elongation or the shrinkage of materials, and the shear strain, which will characterize the shear deformation, so the change in the shape of the material without change in their volume. So we're going to start now by introducing and defining the normal strain, and then we will talk about the shear strain. So to formally define the normal strain, again, so let's consider the same beam here that is attached to a fixed support, and let's assume that this beam initially has a length L0, so this is the initial length of the beam, and you apply, for example, an axial load N to this beam. So this is before the deformation. This is before the deformation is occurring. Now, if I look at what the beam is going to look like after the deformation has occurred, so the beam is going to be now elongated. So the beam is going to have a length that becomes longer than the initial length. So we are going to write L, the new length of the material after the elongation. So now this is after the elongation. And so we are going to make a few definitions. We are going to write delta. This is going to be the absolute elongation of the beam. So this is going to be how much longer the beam is. So we're going to define it as the elongation. So this is now a definition, the elongation of the beam, what we are going to call the elongation. This is going to be a quantity that is a length, which with a unit of meters, inches, centimeters, etc. And the elongation by definition is going to be the new length divided by the old length. So this is what we are going to call the elongation of the beam. This is the new length divided by the old length. This elongation can be either positive or negative. It's going to be positive if the new length is longer than the old length, if there is a tension. And it's going to be a negative elongation. So that's going to be an algebraic quantity. It can be negative, and it's going to be negative if the beam actually becomes shorter after the deformation. If you apply a compression, then the beam will become shorter, and in that case that's going to be associated with a negative elongation. So elongation can be either positive, either negative. And then based on this elongation, so we said that the elongation is not the most meaningful way to characterize how deformed a beam is, because at fixed stress, a beam that is initially longer will exhibit more elongation than a beam that is initially shorter. So if we want to find a way to characterize the deformation and to quantify this deformation in a way that does not depend on the initial length of the beam, then we are going to define the normal strain. And the normal strain, again, this is a definition here. The normal strain is going to be, so we are going to write it epsilon. So this is epsilon. And we are going to define this as either, so the elongation divided by the initial length, or, which is the same, the new length minus the old length divided by the initial length. So that is the relative elongation. In this case, we normalize the elongation by the initial length. That gives us the relative elongation, or the strain. And in this case, because it's a normal elongation due to a normal load or a normal stress, this is what we are going to call a normal strain. In terms of the unit of this quantity, right? So the elongation, its unit is in meter, centimeter, inches, etc. So the international system unit would be meter. And when we talk now about the unit of the strain is in meter divided by meter, so it doesn't have any units. The strain is unitless. It's a unitless quantity. Sometimes you can also refer to the strain in percentage. You can say either a strain, for example, of 0.01 would be a strain of 1%. So you can express it in 1%, but percentage is not a unit. That's just a way of characterizing an elongation with respect to the initial length. So now in terms of the sign, we said that, again, those two quantities, both the elongation and the strain, can be either positive or negative, so they can have a sign. And in that sense, we will use the following sign convention. We will say that if the elongation is positive, that is to say, if the strain is positive, that is exactly the same thing, since the strain is defined as the elongation divided by the initial length. Initial length is always positive, so the sign of the elongation will be the same as the sign of the strain. So if the elongation is positive, or if the strain is positive, this is going to be associated with an elongation. If the beam becomes larger, so the new length becomes larger than the initial length, this is what will happen if you apply a tension. If you apply a tension to your beam, then it will tend to become longer. And then the second case is if you have now a negative elongation or a negative normal strain, then this is going to be associated to a shrinkage. The beam will become smaller, so the new length will be smaller than the initial length, and this is what is going to be caused by a compression. So those are the two, this is the sign convention that we will be using for the strain. Positive normal strains means that you have an elongation. Negative normal strains means that you have a shrinkage. The length is decreasing. Okay, so now same way as we did for the stress, now we're going to define, in addition to the normal strain, we're now going to define the shear strain that will be used to quantify the extent of the shear deformation that bodies are subjected to. So same thing here. Let's take an example. Let's consider this member here that is attached to a fixed support. And let's assume that this member is subjected to a shear force at the top like this. We are going to define, in this case, L naught, which is the initial length of the material. And so this is going to be before the deformation. And we are going to see now what happens after the deformation. So in this case, if you start with the initial beam like this, the effect of this shear stress here is going to cause this member to be sheared. So its new shape after the deformation will look like this. So it's going to be sheared due to the shear load that you apply. So this is what the beam will look like after the deformation. So now the question is, what is the right way of quantifying this deformation? In the same way that we did for the normal strain, we want to find a way to characterize this shear strain in a way that does not depend on the geometry of this beam. And one thing here that we can realize is that if you have a beam that is like this and that you apply a given shear load like this, and if now you consider a beam that is 2 times longer and that you apply the same shear load, the deformation will now look like this. So we need to find, in this case, to find a way to characterize the deformation of this beam in a way that does not depend on the shape, on the geometry of this beam. In the same way that for the normal strain, we define the normal strain as the relative elongation, because in this case, if we use the relative elongation, it does not depend on the initial length of the beam. Now we need to find a way to define the shear strain in a way that does not depend on the length of this beam. And one way that is a universal way of defining the shear strain in a way that does not depend on the length of the beam is to define the strain as this angle here, this angle that we can write theta, which is the angle that the beam is being sheared due to the load that is applied on this beam. Why? Because in this case, even if the beam on the right here is 2 times longer than the beam on the left, this angle here is going to be the same in those two beams. For the same shear load, this will result in the same angle here. When you apply the same shear load, you will get the same deformation if you quantify this deformation in terms of the angle that this beam is making with respect to its initial position. So this is how we are going to define, in this case, the shear strain. So this is a deformation. This is a definition. This is just how we decide to define this shear strain. So we are going to define this shear strain. The shear strain is going to have a different notation than the normal strain. The shear strain is going to be written as gamma, and we are simply going to define this shear strain as theta, where theta is the angle in radians, not in degrees, that the beam is making with respect to its initial position after the deformation. So now, because it's not convenient in practice to measure angle, it's much easier to measure some distances than to measure some angles. We will come up now with a simplified definition, an approximated definition of the shear strain. And for this, what we are going to do is to use the small angle approximation. The small angle approximation means that we are going to assume that because the load that is applied on this beam is not very intense, or because this beam is very stiff, then we can assume that the deformation that this beam is going to undergo is going to be small. So it's going to be reasonably small. And if this deformation is very small, then we can make some approximation. The approximation that we can make is that if theta is very small, then the tangent of theta is going to be very close to theta itself. If x is very close to 0, then tangent x is approximately equal to x. X is the first order of the Taylor expansion of tangent x. So same thing here. If theta is very small, if theta is close to 0, then the tangent of theta is very close to theta itself. So that's the approximation that we will be using. This approximation works very well when theta is close to 0. This is assuming again that theta is expressed in radians. But if theta becomes very large, then this approximation would not hold anymore. So now, because by using this approximation, we can also express what is the tangent of theta. The tangent of theta is going to be the ratio of the opposite side of this triangle divided by the adjacent side of this triangle, because this is a rectangle triangle here. So because of this, we are going to define several quantities. So we are going to define first here the lateral displacement of the beam due to the elongation, due to the shear. So this is going to be delta. And we have already defined L naught, which is the initial longitudinal length of the beam. So we are going to say that tangent theta, this is the opposite side, so this is delta, divided by the initial length of the beam. This is L naught. So that's another way to express the tangent of theta. Tangent of theta, simply by using trigonometry, is the opposite side. This opposite side is the lateral deformation, the lateral displacement of the beam due to the shear that is applied, divided by the initial length, divided by the initial longitudinal length of the beam. So in this case, what matters is the initial length of the beam, which is the length orthogonal to the direction of the shear. In this case, the shear is horizontal, and we are talking about the length that is the vertical length. So in this case, we are talking about the length that is orthogonal to the direction of the shear. Here in this case, the width of the beam has no influence on its shear deformation. The only thing that matters is the length of the beam. If you have a beam that has a small length, then its lateral displacement delta will be small. And now if you have a beam like here, which is longer length, then its lateral deformation will be larger. So what matters is the longitudinal length, the length that is in the direction that is orthogonal to the direction of the shear load. So in this case, what we saw is that we can express tangent theta as the ratio of this lateral displacement divided by the lateral, the longitudinal length L naught of the beam. So on the other hand, since we saw that the shear strain is equal to theta, and since on the other hand theta is close to the ratio of delta divided by L naught, then what we can write is that if this small angle approximation is true, which is going to be the case all the time in this class, we are going to assume that we are always considering some materials that are stiff enough so that the deformation is small enough that this approximation is correct. So in this case, we can redefine the shear strain, or we can simplify the shear strain as being the ratio of delta divided by L naught. So where in this case delta is the lateral displacement of the beam due to the shear. So this is if you have a beam like this and it's subjected to a normal shear strain, a shear load like this. So you define delta like this as the lateral displacement, and you divide by the length, which is orthogonal to the shear load. This is the longitudinal length of the beam, where the longitudinal length of the beam in this case is the length that is orthogonal to the direction of the shear load that is applied on this beam. So another example is if you have a beam like this and you apply a shear load like this, then this beam is going to be sheared like this. In this case, you will define the lateral displacement delta like this, and in this case, the longitudinal length of the beam, L0, is going to be this length here. So in terms of unit, in the same way that the normal strain does not have any unit, it's the same thing for the shear strain. The shear strain does not have any unit. It's a distance divided by a distance, or it's an angle in radians. So it doesn't have any unit, any SI unit, any international system unit. And in terms of the sign, we will use the same convention as for the shear stress. That is to say, in this case, this would be associated with a positive shear strain. And if you apply a shear load like this, which results in a deformation like this, then this would be a negative shear strain. So we will use the same sign convention as the one that we defined for the shear stress last time, where this is going to be a positive shear deformation. This is going to be a negative shear deformation. And this is again the sign convention that we will be using. For example, in this case, this would be a negative shear deformation. Again, this is exactly the same one, the same convention that we used for the shear stress. So now that we have defined the stress in the previous chapter, and now we have defined the normal strain and the shear strain, which is a way to quantify the deformation. Now what we are going to see in the next section is how those two things are related. What is the relationship between the stress and the strain.